Marseille, and he will talk about statistical properties of some random dynamical systems.
Thank you. So first I would like to thank the organizers because this is my last week here and I really enjoyed my stay. So here we go. So actually the title is a little bit a lie because I said I will speak about statistical properties, but I will rather concentrate myself on a single topic, namely concentration inequalities. So the title will be concentration inequalities. I will describe some results on concentration for random and sequential dynamical systems. So first let me give a definition. So suppose that X is a metric space with metric V. We say that the function K from the product Xn with values into R is separately Lipschitz. Lipschitz if it is Lipschitz in each coordinate and with uniform bound with respect to the other coordinates. So we just take x0, xg, xj, xn. We write the difference between this term, and the same way we change only this term. So we change xj into xj tilde xn. And we want this to be bounded by some constant c times the distance between xj and xj tilde. And the constant c should depend only on j, not on xj, neither on the other coordinates. So this must hold for all j and all x0, xn, and all xj tilde. So now, suppose that we have a process, a stochastic process xn, which takes values in x. We say that xn satisfies an exponential concentration inequality if the expectation of the exponential of k x0 until x n minus 1 minus the expectation of this term is less than the exponential of some constant c times the sums of all Lipschitz constants to the square of k. So lib_j of k is just the base constant cj appearing here. And we say that the process satisfies an exponential concentration inequality if this holds for all n and all function k separately Lipschitz. So, and for some, the constant c does not depend on n and does not depend on k. So basically it's just a bound for the exponential moment of k of x0 until x n minus 1. So if we just do the Chernoff trick using this inequality, this has the following corollary, that namely a large deviation estimate. So if this holds, then the probability that kx0 xn minus 1 deviates from its mean by epsilon is less than 2 exponential of minus some constant c epsilon square divided by the sum of the Lipschitz constant to the square. So basically, if we manage to, this decays exponentially fast. So such an inequality implies that we have exponential large deviation inequalities for this quantity. So what's the difference between large deviations, as everyone knows, is just that first it's non-asymptotic. This is valid for any n, even for small n. The constant c doesn't depend on n. And this is so this is the first fact. The second fact is that this is for every k of separately Lipschitz functions. Usually for large deviation estimates, one only use sums, ergodic sums. So this is valid for more general function k. In practice, such functions arise when we, in statistics, for instance, when we have some estimator and we want to estimate how fast it converges to the quantity we want to estimate. So k can be complicated, and even it can be defined implicitly. So we don't have a formula, but one is still able to estimate the Lipschitz constant, and then we are able to estimate such quantities like this. But the counterpart, the price to pay, is that this is less precise than a large deviation principle. We just have an upper bound, which is not sharp. We don't have any lower bound for it. So, okay. So just to state a result, in the ID case, we have the so-called Mach Diarmid inequality. So if xn is ID, well, actually we don't need identically distributed. We just need that xn is an independent process, and it takes values so we endow x with a discrete metric. Then xn satisfies an exponential concentration inequality. Okay, so this is a picture in the ID case. So now we want to discuss dynamical systems. So suppose that we have x, t, new dynamical systems, a probability measure preserving dynamical systems. So yes, the process xn will simply be t to the n, so just the composition of t n times. So we say that the dynamical system satisfies the concentration inequality if this process satisfies this. So this, in the context of dynamical systems, this was pioneered by Collet, Martinez, and Schmidt in 2002. So their results will just follow. Two or three. we have a map T from the interval into itself, which is piecewise T2. Uniformly expanding. And topologically mixing. Under those assumptions, the map T admits a unique, absolutely continuous invariant measure, probability, and so let mu with a unique, absolutely continuous invariant probability. And we assume that the density is bounded away from 0. Then this system satisfies an exponential concentration inequality. So this was the first result, and then follow a lot of works on this kind of subject. So basically, they try to prove the same kind of results for instance, for maps which are modeled by Young Tower with either exponential tail or polynomial tail. For instance, a map of the interval with a neutral fixed point. And actually, a rather precise and complete picture is given by a result by Chazot and Wezel. From 2012. So we'll just state the result, roughly speaking. So suppose that x T mu can be modeled by a Young Tower. So the system can be either non-invertible or invertible. It doesn't make any difference. So we have a Young Tower with exponential resp polynomial tail for the return time. Then the system, in the exponential case, it satisfies an exponential concentration inequality. In the polynomial case, we have a polynomial concentration inequality. I will state how we define it. So then the system
tower is for people.
Okay.
Just two words.
Just in roughly speaking, because otherwise it will take too long. So suppose that you have a system X, which are let's say which is expanding. So just an example, I think it should be easier. So in the result by Collet, Martinez, and Schmidt, the map has to be uniformly expanding. So the derivative has to be strictly greater than 1 everywhere. So let's assume that instead of being uniformly expanding everywhere, we have a point where the derivative is equal to 1. So here, just equal to 1. So the dynamic is chaotic, but when it comes very close to the fixed point, it will spend a lot of time to escape this laminar region and then fall into the chaotic. So it should go the other way. And so on and so on. So basically, we cannot expect exponential mixing. I mean, we have polynomial mixing. So Young tower, just say we can. Okay. So the part of the phase space where the uniform expansion is lost is very localized, just at one point. If we remove some neighborhood of this point, the map is again uniformly expanding there. So the idea is just to select one subset y of x where the map has good properties. So for instance, we take, in this case, a good choice is y 1/2. So let's say it's 1/2, 0, 1. But other choices are possible. But we have y here. And since the map doesn't preserve y is sent to the whole space, but we just consider the first return map of y into itself. So if we take a point from y, we wait until it comes back. This gives a new map from y into itself, which is uniformly expanding this time. We will encounter only points where the derivative is strictly greater than 1. So the map looks like that. The difference between there and there is that we have countably many countably many domains of regularity. But the map is uniformly expanding, and one can prove results for the system on y. And then there are standard techniques to pull back the result from y to results on x. So this is basically the idea behind Young towers. Actually, Young towers, this is not necessarily a first return time. So sometimes we have to wait a little more in order to recover more expansion of hyperbolicity. But the idea is like this. So this is just what we have to keep in mind. And the tail of return time, so if we define R from y into n, this is just the times it takes to a point x in y to come back into y. And so the tail is just the measure of this quantity, how fast it decreases to 0. So either it's exponential or polynomial, and if it's exponential, we have an exponential concentration inequality. And if it decays polynomially, so for instance, this is the case here, it will decay polynomially fast, and the rate of decay will depend on the order of tangency here. Then we have a polynomial concentration inequality. So I will state what it means. So xi of order q greater than 2 if, so here we have a bound for the exponential moment, centroid exponential moment. Here we will require a bound for the polynomial moments. So if the expectation of the polynomial centroid polynomial moment of k, x0, xn minus 1, minus the expectation of this takes the q's power, and this has to be less than some universal constant which doesn't depend on n, neither on k, times the sum of the Lipschitz constant to the square, and this has to be to the power q over 2. So again, this can imply the large deviation estimate, but this time this will decay polynomially fast. Okay.
With this theory, you can relax the assumption that the density is bounded from 0.
If you can, the problem is how
Yes,
are you able to build a Young tower with exponential tails for this kind of map? If you relax this assumption, I don't know.
yes, for instance, if you take Lorentz map, if you take Lorentz
Yes, for specific systems,
of course,
you mean.
yeah.
But in field generality, I don't know. There is your result with Alves and Lusato, but again, you have to assume that the density is bounded away. So maybe it's unnecessary, I don't know. Okay, So all of this was done for deterministic dynamical systems. Nothing or almost nothing was known about random systems. There is only one result available, as far as I know, but it concerns like observational noise. It's done by Maldonado, so I will just describe what he. Okay. What he proved. So let again be x t mu be a dynamical system, and assume that x is a subset of Rd. So now let's take a sequence Ck, a sequence of RID random variables, again with values into Rd. The process we consider is just xn is Tn plus Cn. So here's randomness doesn't affect the dynamics. It just affects the observation we are doing of this dynamics. So Tn still evolves according to the law of T, but when we observe it, we have some noise, which usually is quantified with some epsilon, which is basically small, but here we'll take epsilon equals to 1. It doesn't matter for us. And so the result of Maldonado is following. So 2012, I guess. Yes. So the assumption is that if this system satisfies either an exponential or a polynomial concentration inequality, under some reasonable assumptions on this sequence, this process again satisfies the same kind of concentration inequality. So suppose that. And so the assumption is that this sequence is bounded in infinity. So this doesn't cover the case of a sequence of Gaussian random variables. So it's still open. But if it is bounded into infinity, then Xn satisfies the same kind of concentration inequalities. Just concern observational noise. So if we are really interested into random dynamical systems, we have the following. So just let me recall what random dynamical systems is at least in this talk. So suppose that we have a family of maps. So let's say it's a finite family. So we have a finite number of map Ti acting on X and let, and we have a probability vector. So the process is constructed as following. We take x0 distributed according to some probability mu, and then we define xn plus 1 as Ti of xn with probability pi. And this is done, so each time we throw dice and with probability pi to find I. And so this gives rise to a Markov chain with initial probability mu. So with probability I. So we apply Ti to the previous state with probability Pi, and this is done in an independent way. So we say that mu is stationary if it is stationary for the Markov chain. So each xn is distributed according to mu. So the result we proved is just an extension of what I erased right now. We have a family Ti of maps which satisfies the assumption of Collet, Martinez, and Schmidt. So they are piecewise C2 uniformly expanding maps of the interval. So suppose here that x is again 0, 1. That each Ti is piecewise C2 uniformly expanding. So we assume, so under these conditions, we know that there exists at least one stationary measure which is absolutely continuous with respect to the bag. So we assume actually that there is only one such measure, a unique, absolutely continuous stationary measure mu, which is mixing. So we assume it is mixing. Otherwise, we can rule out we can just restrict to one mixing component and rule out the others. So we can assume it is mixing. And again, we assume that the density is bounded away from 0. So d mu over the bag is greater than some constant greater than 0. So this kind of assumption can be satisfied if we have some covering properties for the maps. So since this is true, it is the case if for every non-trivial summate interval of 0, 1, we can find an integer n and a sequence omega 0 omega n minus 1 belonging to 1 to L, such that T omega 0 of y. So if we apply T omega 0, then T omega 1 up to T omega n minus 1, we have the whole interval up to a finite number of points. So this is called covering type assumptions, and this implies that we have a unique absolutely continuous stationary measure which is mixing and whose density is bounded away from 0. So for this, I will denote this by T omega bar n. So omega bar is the sequence omega 0 up to omega n minus 1. And I will denote this concatenation of different maps like this. Under these assumptions,
so if you have one map covering,
yes, if one map is covering, then the random system is itself covering. So for instance, if we have the doubling map, it's covering. actually it's some kind of topological mixing assumption for the random system. And so the result. So we consider the process. The process is already different. The theorem is from myself, Mad Nicole, and Sandro Vaganti from 2013. Under those assumptions, again we have an exponential concentration inequality for the process Xn. Namely, we have the expectation. So the expectation is taken with respect to P, which measures the probability of having applied this map instead of another. And mu is the density of the stationary measure. So in some sense, it is an annealed result. It holds once we average over all possible sequences.
Do you really need in your theorem to have all the maps uniformly expanding, or
Yes.
can I do it with
We use the spectral gap on BV,
expanding
but
on average?
it's not enough.
It's not enough.
We have tried, and I think it's true. We don't need each map to be uniformly expanding. We just need, I believe it's true if the system is expanding on average, but we were not able to prove it.
Okay.
So we need, again, some distortion. Okay, yesterday, we cannot do it. So just let me give you an application. So this concerns the empirical measure. So we define the empirical measure like this. So we have an initial condition x and a sequence of map we are iterating, and we just form the average of the Dirac point mass at each point of the orbit until time n. So we have an orbit, we track it until time n, and we just average in order to get a probability measure again. So this is a probability measure, and from our Birkhoff ergodic theorem, we know that this measure converges weakly to the stationary one for almost every x and omega. We have that the n of x omega goes weakly to mu for almost every x and omega. So for statistical purposes, we are interested in the speed of convergence for this. So this is where concentration inequalities come into play. So I have the following proposition. So first, we need, in order to show how fast this converges to this measure, we need to quantify how far they are from each other. So there are several ways to do it, and one way is to introduce the so-called Kantorovich metric. So since here we are interested into one-dimensional probability measure, this metric has a particular simple form. So if we have two measures, probability measure mu1 and mu2 on the unit interval, the distance between the two is just the L1 norm of the difference of the two cumulative distribution function. So usually it's defined as a sup over all the difference of the integral with respect to the measure of one Lipschitz function. But here we have this particular simple form. Okay. Where f mu y of t is just the measure of the interval 0 t. So this is the L1 norm between the difference of the two cumulative distribution functions. And so in this metric, we can prove that there exists some c and some t0 such that for all t greater than t0, the probability of the set of all x omega such that Kantorovich distance between the empirical measure and the stationary measure greater than t over square root of n. This decays exponentially fast with respect to t in the Gaussian way. So that's the sketch of proof. So we define the function k of x0, xn minus 1, just the integral 1 over n, sum from k and from 0 to n minus 1. It's characteristic function of the interval 0t applied to xk minus the cumulative distribution function of the stationary measure, and we integrate with respect to t. So if we apply k to the process, the Markov process we defined before, capital X0, capital Xn minus 1, we exactly get the Kantorovich distance between the empirical measure, x omega, and the stationary measure. So if we want first, if we apply concentration inequality, it's easy to see that this function is Lipschitz, separately Lipschitz, and that the Lipschitz constant of R of order 1 over n. So we can apply our concentration inequality and get that the probability of the x omega such that k x0 x omega. So let me drop the x omega. So the probability is that k x capital X0 capital X minus 1 deviates from its mean by t over square root of n. If we apply the result I gave a while ago, we get some c t square. Yes. And so now we just need to estimate this mean. Basically, so we just need. So concentration inequality just says that this is very close to the mean. Now we have to estimate the mean. And this can be done using decay of correlations. So I will skip this part. It's not of interest for us today. show that the mean of this function is of order 1 over square root of n. So we just put in the two assumptions together and we get the result. So this is one application among many others. So I just want to come back to here. As I said, this is an annealed result. It doesn't say anything if we just forgot P. Do we have such a result that if we fix omega, so we fix a realization, a fixed concatenation of maps, do we have same kind of result? With maybe the constant C, the constant C could depend on omega or not, I don't know. But can we prove such a result? Actually, we were not able to do it, but we have some result related to this. So this is in context of sequential dynamical systems. Sequential dynamical system is just, instead of applying the same map over and over and over, we apply different maps, but for a given fixed sequence of maps. So this is in a non-autonomous dynamical systems, but a discrete time non-autonomous dynamical system. We have a sequence of map Tn, and we apply them. So the law of evolution is different at each time. So let Tn be a sequence of maps Tn from x to x. So in this context, we don't have anymore an invariant measure. Unless we are in a very specific situation, it's not necessarily true that all the maps Tn will preserve the same measure. So we don't have an invariant measure, but instead we have a quasi-invariant measure. Namely, we can assume that all maps Tn are non-singular with some fixed probability measure. With respect to fixed probability measure. So what we have to keep in mind is just a case of piecewise smooth maps, and n is just the Lebesgue measure. So here, usually quenched results say that for almost every realization we have the result, but it's an almost sure result. It holds for typical sequences omega, but if I give you one sequence, one cannot say whether it's generic or not. In the context of sequential dynamical system, we are interested to checkable conditions on the sequence in order to ensure the limits theorem to hold. So usually we put strong assumptions on the sequence. For instance, all maps are closed to a fixed one, or some different kind of hypothesis. But again, we have to assume something strong about the map, the sequence of maps. So here, okay. So again, we will consider maps on the interval x is again 0, 1, n is the Lebesgue measure. And so let's consider the following class of map. Let's see the class of maps C from x into x. We have a bunch of assumptions, namely, so all maps are uniformly expanding, but we need a uniform bound on the expansion. So there exists lambda strictly greater than 1, such that t prime of x is greater than 1 for all x and also for all t in the class C. So we need also a uniform bound for the distortion. So we just not necessarily, the map itself has to be of bounded distortion, but the coefficient has to be uniform with respect to t. So if we take, usually we say a map has bounded distortion if the supremum of the second derivative over the square of the first derivative is bounded by some constant m. But here we assume that the constant m doesn't depend on the map t. So these two first assumptions. So they are piecewise maps. Piecewise smooth. We also assume that we have a uniform bound on the number of domains of monotonicity. You cannot have a larger and larger number of domains of monotonicity. So 3, there exists m, so that the number interval of monotonicity and regularity also. Monotonicity of t is less than m, and this for all t in C. So until now, those assumptions are reasonable. We just take a fixed map T, a map, and all maps which are in some convenient neighborhood of this map T, and it holds.
But two different maps could have different the number of intervals of monotonicity, or
Yes. No, not the same. This can be, you can use two, for instance, you can use 2x over mod 1 and 3x mod 1.
Then refine.
Sorry?
Then you refine, you take a common partition.
Yes, for instance, we can take a, not necessarily, because there are infinitely many maps. So if we refine take the common partition, we doesn't make sense. No, but the number has to be bounded independently of the map.
Oh.
So we cannot have more than m interval of monotonicity, but they are necessarily shared by all the maps. So those are reasonable assumptions. And the fourth assumption is the so-called loss of memory. So, okay. So usually in mixing dynamical systems, we have decay of correlations in the sense that if we write this integral g f composed with tn d mu, if the system is mixing, this will decorrelate and goes to g d mu, f d mu. And usually, if we have some good properties, one is able to estimate the speed of this convergence for smooth enough observable g and f. Here we don't have anymore an invariant measure, so we have instead this tn composed until t1. So for simplicity, I will denote this by t1 up to n, and this doesn't converge. But again, this, if the system is mixing enough, mixing, it doesn't converge to something, but it decorrelates. And so this difference can decay to 0 when n goes to infinity. So it doesn't converge to a fixed number, but it decorrelates. So the integral of the product is closer and closer to the product of the integral. And here we have to keep t1 up to n because it doesn't preserve m. Here it should preserve n. So usually one should put tn, but it disappears due to the invariance. And so usually loss of memory is just an estimate of this quantity, how fast it decreases to 0. So So just to say so that it doesn't go to a fixed number, but it's attracted by a moving path instead. So the density, we start from a density with respect to m, and you let it evolve under the dynamics. It won't converge to a fixed density, which is the density of an event measure. But if you start from two different densities, they will get closer and closer as the time goes to infinity. So here, the loss of memory properties. So it's rather technical to state, but the understanding is there basically. So there is some constant c, some theta less than 1, such that the BV norm, so I will introduce the notation after. The BV norm of Pn of f is less than c theta n times the BV norm of f for all f in BV with mean 0. So what is pi n? Just the concatenation of the transfer operator of the maps. So we have transfer operator for each map T. We have a transfer operator P of T, which acts on L1 functions. So if we have some initial density F and we apply the map T, then the density goes to P T of F. So the transfer operator is defined like this, and Pn is the concatenation of the transfer operator of T1 up to Tn. So just the transfer operator of T1 to n. And so we assume this for all f with 0 mean and all sequences T1, Tn in the class C.
Basically, we have to control the L1 norm and the total variation.
Yes, the L1 norm and the total variation. For instance, this holds if we have a single map which has which is uniformly expanding and mixing. Because from Lazo-Tayork, we know we have a spectral gap on BV, and here we just have P to the power n, where P is the transfer operator of the map. So since we have a spectral gap, here we have a function of mean 0, so it doesn't have, we have 1 which is simple, and the rest of the spectrum is away. Since f doesn't have any component in this eigen space, its norm decays exponentially fast. And here it's an analog statement, but in the context of sequential dynamical system. So we cannot apply directly spectral theory because it doesn't make sense for the concatenation.
Polynomial decay of this quantity is not enough.
But the problem is that we really need also functional norms. If you have our kind of result in the polynomial case, I don't know what to do.
Also, like you explained, in the case of deterministic map, you need the map to be mixing for this to.
Yes.
Right.
Yes.
And what's the equivalence here?
That's a good question. Mixing is just, we can define mixing like this. We say it's mixing if this quantity goes to 0 for all G and all F in L1 and infinity. It's the definition of mixing. But how to check it concretely, it's another story. But that's a natural extension of the standard theory for autonomous systems. So basically, this implies mixing as a, because this is for using the transfer operator, one can write this integral like some G Pn of G minus G dm times F dm, and using, if G for instance is of mean 0, this goes exponentially fast to 0 in the BV norm, and so in the L infinity norm, and then this goes to 0 exponentially fast. And this holds for a dense class of observables, so it is mixing. But here it is stronger than just mixing. It's exponential mixing, and we need to have the BV norm on both sides of the inequality. So this is rather strong, but there are several classes of maps which satisfy this. So 1, 2, and 3 are standard. It's easy to check whether it holds or not. And 4 holds for instance, if C is a convenient, so convenient has to be defined, convenient neighborhood of a map, single map T, which satisfies the hypothesis of Collet-Martinez-Schmidt. So it has to be uniformly expanding and mixing, basically. And this was shown by Conze and Rossi in 2007 of map T. So the map T has a spectral gap, as I described in the top out. So convenient neighborhood, one has to estimate, for the one which are familiar with this, one has to estimate the triple norm of the difference of the transfer operators. So basically, we put this distance, which is just, so no, it's the beginning of
and measure and add one.
yes. Okay. And the sub over all f in dv will be less than 1. So for instance, if we put this distance of the set of maps, which are piecewise C2, and if we have a map T which has a spectral gap on dv, so it's uniformly expanding, it is topologic mixing, then a convenient, a small neighborhood for the distance of this map will satisfy all these assumptions.
So you will basically retain spectral gap for all these.
Yes, but yes, also. Okay. So usually one has a scored metric on the space of maps, which is usually easier to handle than the triple norm. Okay. So here is the hypothesis. Okay, so it's time to conclude. So the result is again that in this situation, we have an exponential concentration inequality for this map. So the process here is just xn is tn composed up to t1 and theorem. So this is a result of myself and Jérôme Rousseau, 2013, under these assumptions. We have an exponential concentration inequality again. So just to state a few open questions. So the quenched version is not proved. We don't know whether it holds or not. So it would be nice to prove it. So again, as you mentioned, for the case of random systems or for the case of sequential systems, the question is open. If we have polynomial decay of correlation, of polynomial loss of memory, can we prove polynomial concentration inequality? We are not able to do this because in order to prove polynomial concentration inequality, one uses again the scheme of Young Tower, and this doesn't make really much sense. The sequential dynamic in the sequential context doesn't really make sense. In the random system, one can maybe use this kind of skew product, but it's not really easy for us. And so, what's open? So yes, I will stop here. Thank you.
Any questions?
I have one more question, but do you really believe one needs a spectral gap, or is enough to get this kind of decay eventually polynomial for condition 4.
You mean this?
Because
What do you...
I mean, the point is, if you have a spectral gap, I suppose you get this kind of.
Yes, but spectral gap is not clear for concatenation what it means.
No, for the single map T.
For the single map, yes.
Yes, but if we take, for instance, map for which you don't have spectral gap, but we can prove this kind of decay eventually polynomial, is enough for the theory or not?
In the BV norm?
Yes. If I can prove this.
Yes, I think.
Eventually
No.
polynomial in the BV norm, we don't need the spectral gap, right?
Yes, but usually you don't have BV in both sides.
I know this. I know.
Even for a iteration of a single map. So, I don't know. And is it enough even if we have this?
I mean,
Which
you
is
told me that
reasonable.
the cause origin use this condition Pn1 blah blah blah.
Oh, yes, thanks for reminding me that. I forgot there is one more assumption here. Thanks. So just to say that we have 5, which is that this transfer operator Pn applied to the function 1 should be greater than some delta greater than 0. So this is uniform for n large enough. So this limits a lot the applicability of this result. But Conserology, in their papers, they use this kind of assumptions, and they were able to prove it holds. For instance, if we have a sequence of beta transformations with beta n close to a fixed beta. And
some kind of covering definition.
I tried to use covering because it's reasonable to use covering to prove this, but no. We tried, but it didn't work.
Okay, thank you very much.